Dear all, in this session, we will learn how to conduct watershed analysis in QGIS. Following the learning, we will understand basic knowledge of watershed analysis and how to apply analysis results in planning and design. The module consists of 3 steps: data acquisition, analytical operation, and results interpretation. The technical route is displayed on the screen. Briefly, we must first extract the necessary raw data, then analyze it to obtain the initial results and visualize them as final results, and finally interpret the final results. Step 1 is data acquisition. To collect the data, we will introduce a website called Geospatial Data Cloud. Of course, there are other websites that can provide the data we need, but this is the free and easily accessible one. The site link has been displayed on the screen. Please be aware that we will need to register the first time we use the site. After entering the site, we'll need to use the advanced search section. First, we must select a dataset. For our learning, we simply require Aster GDEM data with 30-meter resolution. For detailed knowledge about DEM data, please refer to the video of Module B 1.2. Next, we need to set the location. In this case, we use the administrative location to pinpoint Shatan in Hong Kong. Of course, we can decide the place by drawing a rectangle or a free shape. After choosing a place, click the search button. The screen will then display the data covering our location. To download the data, we may simply click the down arrow. Then we need to download an administrative boundary document. We utilize the Ali Cloud platform in this case, and the screen displays the website link. However, if we already have a vector boundary file, we can skip this procedure. After entering the website, simply zoom in to find Hong Kong. Pinpoint the Shatan district, and its URL will display on the right. Simply select GeoJSON and copy the URL. Then we must go to a web page called MapShaper, where we can simply paste the URL, use the shortcut key Control V to view the boundary. Following that, we must export the border in shapefile format. Step 2 is analytical operation. First, we need to create a new project. Click New after selecting the Project button on the toolbar. Following that, we need to install the plugins required for this analysis. Select the Plugins option on the toolbar and then select Manage and Install Plugins. We may use 3 plugins: Grass GIS Processing Provider, Grass 8, and Processing Saga, Next-Gen Provider. I have already installed all of them. If we want to install them, simply switch to the Not Installed button and search for them. We can now load the DEM data to the new project. We simply need to drag the image displayed in the browser frame to the layer frame. After that, place the mouse arrow on the targeted layer and click the right mouse button to access the properties to check the information. Pixel size and CRS are the key details to check. The former ensures resolution. The latter confirms the coordinate system, Universal Transverse Mercator Zone, i.e. UTM zone, and projection. In our case, the coordinate system is WGS 84, and the UTM zone is 49N. If we want to modify the display style, go to Symbology and select a preferred color style. Now, we must import the boundary file into the layer frame. We'll use it to trim the DEM data. Simply select the Raster option, then Extraction, and click Clip Raster by Mask Layer. The input layer is our DEM layer, and the mask is the boundary layer. Set all options and click Run. We now have DEM data with the boundary of the Satin district. We must export it to make it a permanent file. Now we can start the watershed analysis literally. The first process is to fill the sink. It is used to remove incorrect depressions in DEM data in order to maintain continuous surface water flow. To open the module, simply type Fill into the search box in the Processing Toolbox frame and look for Fill Sinks, Wang, and Liu. After opening the option interface, select our DEM data and specify the minimum slope, which in our case is 0.01. We only demonstrate the filled DEM as a processing result here, but we can show all of the outputs. Following that, we can start the watershed analysis. In this process, we need to switch to Saga Next Gen in the Processing Toolbox frame, locate terrain analysis, channels, and select channel network and drainage basins. After opening the options panel, we must upload the filled DEM into the elevation box and set the threshold. Please keep in mind that the threshold is automatically filled. If we want to change it, the lower the number, the smaller the basin area. Similarly, we can choose to open all of the outputs, but the must-keep outputs are drainage basins and channels. Finally, we will get the results, including drainage basins and channels. We must then understand and interpret the results. Before we can interpret the data, we need to modify the visualization of drainage basins and channels. We can start from the channels. We need to first classify the order of it. Put our mouse on the targeted layer and click the right button. Choose the properties. In the symbology section, access the categorized. Under the categorized section, we need to choose order for the value box and then set a preferred color style. The screen displays that the order of channels includes 3 levels. After selecting one option, we can move our mouse cursor to the symbol box and adjust the line width and other properties. The channel order is then shown with different colors and line widths. For the basins or watersheds, we still have to select the targeted layer and access the Properties section. Under the Categorize section, select ID for the value box. Then, similarly, we must select a preferred color style. We may also alter the transparency or opacity of the layer. Finally, we have visualized drainage basins and channels that can be easily interpreted. The common rules of the channels include 1. The channels depict the flows of natural drainage rather than actual rivers. However, if a river exists in the real world, there must be a corresponding channel indicating its presence. 2. The greater the order, the larger the channel. That is, channels of lower order always confluence with channels of higher order. Third channel networks do not always follow an exact in-order sequence. For example, Order 1 channels can sometimes confluence directly with Order 3 channels. We can understand it by looking at the image on the screen. By the way, the channel networks can be used to identify potential flow paths, which helps with drainage system planning, river restoration, flood analysis, and so on. The common rules of the basin patterns include 1. Each basin is a hydrological unit with just one outlet for runoff. However, each may have multiple inlets. 2. Sub-basins on the same network branches can be integrated into a bigger basin, but sub-basins on different network branches cannot, as demonstrated on the screen. 3. In theory, basins can be dissembled infinitely. However, to balance efficiency and accuracy, we always use empirical thresholds, and the tools will automatically provide a suitable threshold during analysis. 4. If we can only get DEM data with a 30-meter resolution, the minimum basin area is usually 0.1 to 0.5 kilometers square. Please note that the initial results only show the natural state of channels and basins. In actual projects, if there are noticeable infrastructures such as on-ground highways, mega buildings, large-scale channels, and so on, the streams and basins must be modified accordingly. However, because we are neither hydrologists or infrastructure engineers, our findings are sufficient to assist us understand the hydrological conditions of the proposed sites during the planning and design processes. Finally, to use the analysis results effectively, we can summarize the following content. Things that we can learn directly from the analysis results include 1. The channel networks and watersheds of a specific area. 2. The order and the flow directions of channel networks. 3. The outlets of watersheds and subwatersheds. In a nutshell, understanding the site condition from a hydrological perspective is a key insight we can extract for urban and architectural design. To export our results, we must first create a layout. Click Project and choose Layout Manager. Click the Create button and name the layout. Now we have a new layout. Click the Add Map button to load our results. Thereafter, put our mouse arrow on the map and click the right button to choose Page Properties. Then we can set the map size. If we like, we can also add a legend, a scale bar, and a north arrow by clicking their buttons, respectively. After setting all options, we can export the map in the following formats. image, SVG, and PDF, according to our needs. Finally, these are merely the fundamentals of watershed analysis. If you are interested in learning more, you may do so by visiting the official QGIS website, which is linked on the screen. Thank you for watching. Hope this tutorial is helpful to you.